Do you guys play like Wordle and Connections and all those like New York Times games ever? What? Like Wordle and what? They released a new one yesterday. It's like it's kind of like a word search. Like so that you have like a grid of letters and there's like basically a theme to all of the words that are in it, and you don't just have to go in straight lines. It just has to be like I don't know. There's some underlying graph that they have in mind that you're of like where you're allowed to go. But yeah, so they're like connected. And the whole puzzle gets filled with words and they all follow a theme. So one of the words itself is like the title of the category. And then like all of the rest of the words like sit in there.
Should they not give the theme initially? You have to discover what.
No, they give you like a really vague hint about what the theme is, and then you have to figure it out. And then like once you figure out what the theme is, it's like really easy to find the words, but before you know anything, it's like, yeah, it's really hard. It's fun. Yeah, so the first one was yesterday and there's another one today.
Do you remember what that game's called? That's okay.
It's like, no, I don't remember what it's called. I think I had it open on my phone earlier. It's called Strands. You guys play Connections? It like enrages me every day because it's either like really, really easy and then you're just like, I don't know why I wasted my time doing this, or it's like hard. And the reason why it's hard is always annoying. Like you just didn't know one of the words could be used that way, or like the category is too obscure or something. Okay, let's go ahead and get started. So I've started looking at the midterms. I've graded like 5 of them, so I've barely started, but I've so far been like really impressed with like what I've seen and what you guys did. So it's very cool to see like the submissions and everything. I'm probably gonna finish this week grading them. And when I do, I'm gonna send out a survey just to kind of get your opinion on what you all thought of the midterm, because it was like definitely unusual and probably different from other midterms or like things that you've done in the past. So I just wanted to get your opinions about yeah, just what you thought of it, and if you felt like you got something out of it, or if you feel like you hated it or whatever. So I'll send out a survey like later this week. So today we're gonna talk about connectivity in graphs. We're still kind of blurry. So there's going to be 2 kind of versions of connectivity. One that's looking at deleting vertices and seeing how many vertices do you have to delete before the graph becomes disconnected? And then the other one is going to be the same thing, but for edges. So we'll talk about the vertex one first and prove some things about it. And then we'll get into the edge one. We'll also talk about how they're related to each other. So just start with A definition. So a vertex cut. Or sometimes it's also called a separating set. Of a graph G. Is a set S. Which is some set of vertices such that G minus S has more than one component. So we have some set of vertices and we delete those, and what's left is no longer connected, then we'll say that's a vertex cut. Yeah.
We assume that G is connected.
No, but I guess then every subset of the vertices is a separating set. Okay. And then the connectivity of G. Should I just I think I just started in the middle of the page. That's okay. The connectivity of G, which is written as kappa of G. This is going to be the minimum size of a vertex cut. So this is the minimum size of a vertex cut. Or, okay, so this is basically what it is, but there's like kind of one other thing that can happen. So this is the minimum size of a vertex set S. Such that G minus S is disconnected. Or if what's left only has one vertex. And we'll see an example to see why we want to include that condition. And then you'd say that a graph is K connected if its connectivity is at least K. Okay, so the first thing that we're going to do is a couple of examples, but are there questions before we get into examples? Okay, so for the examples, I'm going to ask you all to compute the connectivity of a couple of graphs. So first, what is the connectivity of Kn? And let's also look at the connectivity of the complete bipartite graph KMN. Okay, so what's the connectivity for KN? Yeah, so this is gonna be, oops, so kappa of KN is n-1, and that's why we include that, that extra condition, so, just going back, uh, if it's disconnected or only has one vertex, just because of the complete graph. So if the graph is not a complete graph, then what can we say about the connectivity? Yeah, so this has to be less than n-1, and why? Mhm. Yeah, so okay, so there's, if G is not Kn, then some edge is not present, right? So then let's look at those two vertices and delete all of the other vertices. Then that's a disconnecting set of size n-2. So so that tells me that the connectivity is at most n-2. So I'll just rewrite this as less than or equal to n-2. It's the same thing. Yeah, so Kn is the only one that has connectivity n-1. Okay, and then what about Kmn? What's the connectivity there? Yeah. Yes, this is just going to be the min of m and n. Yeah. Oh yeah, so that's the complete bipartite graph where you have like one partite set has m vertices and the other one has n, and then you just fill in all the edges. Yeah. Yeah, so to disconnect the graph, you would have to delete all of the vertices in one of the two partite sets. And so whichever one is smaller is going to give you the connectivity. Okay, are there questions about these two examples? Okay, so the next thing that we're going to do is we're going to prove a theorem of Harari that tells you the minimum number of edges that a K-connected graph has to have. And it uses this construction of these things called Harari graphs. So I'm going to define those now, and then we'll show that their connectivity, that they are K-connected, and that they have like the minimum number of edges possible. So let's start. We'll do Harari graphs. Okay, so given two numbers K and N, where K is less than N, we're going to construct a graph as follows. So I'm going to place the N vertices around a circle equally spaced. Okay, and then there's a couple of cases depending upon the parity of K and N. So if K is even, so if K is even, what you're gonna do is we'll form edges by making every vertex adjacent to the K/2 vertices in either direction next to it. So I'll write that down. If K is even, make each vertex share an edge with the K/2 vertices to either side of it. Okay, so let's draw a picture for k is equal to 4 and n is 8. So I'm gonna put the vertices around a circle. And I'm gonna give them names just for the sake of discussing this. Okay, so which vertices should I connect 4 to? Yeah, so k over 2, or sorry, yeah, k over 2 in this case is gonna be 2. So I'm gonna connect 4 to the 2 vertices to its right and the 2 vertices to its left. And then I'm gonna do the same thing for every vertex. So 5 gets those two. 6, we've already done the ones to the right. Okay, is this looking good? It connects it to like, so going back to this one, we have like exactly k over 2 to the right and exactly k over 2 to the left. Yeah. Other questions? Okay, so then here's how you do it in other cases. This is going to break down into 3 cases. So if k is odd and n is even, then we're going to form edges by making each vertex adjacent to the nearest k minus 1 over 2 vertices in each direction and to the vertex opposite it in the graph. So make each vertex share an edge with k minus 1 over 2 with the k minus 1 over 2 vertices to either side of it and the opposite vertex, which exists because n is even. So for this one, I'm going to do k equals 5 and n equals 8. I'm going to try and do a better job spacing the vertices around. Okay. So okay, so now what do I connect 4 to? Yeah. So we get k minus 1 over 2 vertices to the right, k minus 1 over 2 vertices to the left, and then also the opposite one. Okay, so we get kind of a similar picture as before, but we're also adding in the diagonals. Okay, so I need that, and that. Okay. So again, the goal of this is to make like what purpose do these graphs serve? They are going to be k connected with the minimum possible number of edges. So I know these constructions seem kind of weird and random, but like that's the goal that we're working towards. Okay, so then the last case, so we dealt with k even, we dealt with k odd and n even. So the last case is when they're both odd. Okay, so if k and n are both odd, So this has kind of a weird description, but I'll say kind of like what this like intuitively what this boils down to. So we're going to index the vertices by the integers mod n. And then I'm going to construct HKN from HK minus 1 n. So this case we've already dealt with by adding the edges I is connected to I plus n minus 1 over 2 for I going from 0 to n minus 1 over 2. Okay, so let's do the k equals 5 n equals 9 case. So first we have to start by drawing the k equals 4 n equals 9 one. So I'm gonna put 9 vertices around here in a circle. Okay, so I'm gonna start by drawing this case. So that was the simplest case. We just add 2 edges in either direction. So for each one, I'm gonna add the 2 edges in either direction. So I end up with this cycle on the outside. And then all the pairs like this. Okay, so that's HK minus 1 n. And then now I also need to add in some other edges. So let me label the vertices. Okay, so what other edges do I need to add to this? So for example, like based on this condition, what should the vertex 0 be connected to? Yeah, so we'll add in that edge. And then what about 1? Yeah, so we'll connect 1 to 5, and then 2 to 6, and 3 to 7, and then 4 to 8. And we stop there because we're only going up to I less than or equal to n minus 1 over 2. Okay, so that's the k equals 5, n equals 9 case. Okay, are there questions? Okay, so now that we've written down the construction, let's prove the theorem. So the theorem says that the minimum number of edges in a k-connected graph on n vertices is gonna be the ceiling of kn over 2. And furthermore, the theorem is also going to show that kappa of HKN, these graphs that we just made, is equal to K. Okay, so let's go through the proof of this. Are there any questions before we start the proof? Okay, so let's let G be a graph with connectivity K and n vertices. Okay, so the first observation that I want to make is that if I took one vertex and I looked at all of its neighbors, deleting that set of neighbors would disconnect the graph because then that vertex would be isolated. So deleting the neighbors of a vertex disconnects the graph. Oops. So since the graph has connectivity K, that tells me that every vertex is adjacent to at least K edges. Just say every vertex has at least K edges. Okay, so then we can do a count. So if I know that every vertex has at least K edges, what's the minimum number of edges that there could be? Yeah. Yeah. So yeah, so just by like kind of handshaking again. So I have n vertices. Each one has at least K edges. So there's K times n vertex edge incidences, but then each edge is contained in, or each edge contains 2 vertices. So we have to divide that by 2. And then, so whatever this number is, there has to be at least that many. So it'll be the ceiling of that. Oops, not divided by K. Divided by 2. So that means that, so just by counting, maybe I should write more. So by counting, there are at least this many edges. Okay, so that shows us that kind of the first part of the statement, that the minimum number of edges in a K-connected graph on n vertices is this many. And kind of additionally, the Harari graphs have that many edges and are also K connected, so that bound is sharp. So now let's show, so for part 2, we have to show the kappa of HKN is equal to K. Okay, and for this part, since the construction is different for each of the, we have those like different parity cases, you would have to prove each one individually, but the proofs are all somewhat similar, so I'm just gonna do one case. So we'll just prove the case when K is even. So do the case when K is even, and the other cases are similar. Okay, so let's let G be H KN, where K is even, so I'll call that number 2R. Then the minimum degree of a vertex in G is what? Should I go back to the construction? So going back to this, what is the degree of the vertices? Yeah, because we connected it to K over 2. Every vertex got connected to K over 2 guys to the right and K over 2 guys to the left. So in total, we have every vertex has degree K. So we have that kappa of G is less than or equal to K. Okay, why is that? Yeah. Yeah, so the neighbors of a given vertex give you a disconnecting set of size K.
There's like worst case scenario. I was saying less than or equal to something that we can do a better size, smaller size set.
So we'll argue that we can't do better for this graph, but yeah, so the fact that we have a disconnecting set of size K means that whatever the smallest disconnecting set is, it's gonna have size less than or equal to that, yeah. Okay, so now to prove equality, we'll just prove the other inequality. So what remains to show is that kappa of G is greater than or equal to K. Okay, so to do this, we're gonna take any subset S of the vertex set of size less than K and prove that G minus S is connected. So given S subset V of G with the size of S at most K, we're gonna prove that G minus S is connected. Does that make sense? So what this is saying is like, anytime I delete fewer than K vertices, I still have a connected graph. So that means that the connectivity is at least K. Other questions? Okay, so then to show that so we want to show that G minus S is connected. So I'm just going to take two vertices and show how to get a path between them. So given, so let's consider two vertices, U comma V, in the vertices minus S. Okay, and I'm actually just I'm gonna grab this picture. So this was our original graph. Potentially we've deleted some vertices, or we have deleted some vertices. And let's say, like this is U and this is V, for example. Okay, so the original graph had a clockwise path from U to V and a counterclockwise path from U to V. So we have like this path, and we also have this path. So the original graph had a clockwise and counterclockwise UV path. Okay, so let's call the two sets of vertices along those paths A and B. So we have like the red set of vertices A and the green set of vertices B. We'll call the internal vertices on these paths A and B. Okay, now my claim is that since S has size at most, since S has size at most K, I've deleted at most K over 2 vertices from one of A or B. So in S, I'm deleting some number of vertices. And in one of those two sets, either A or B, I've deleted less than K over 2 things. So let me just write out the full statement and then we can convince ourselves. So one of A intersect S or B intersect S is smaller than K over 2. So maybe the easiest way to see this is like almost just by contradiction. So A and B are disjoint, right? So if this had more than K over 2 things and this had more than K over 2 things, then S would have more than K things. Is it making sense? So one of these two things is smaller than K over 2. K in this case was 4. So to continue with the picture, I'll say my S is going to be these purple vertices. Which is less than 4. Okay, so one of these two is smaller than K over 2. In this case, it's the B's. Then, since each vertex in G has edges to the next K over 2 vertices in either direction, so like, for example, 6 has vertices here and here. Even though I've disrupted this path by deleting the purple vertex, there is a way to go around it. So, since each vertex has edges to the k/2 vertices, I'll say k/2 next vertices to either side, deleting fewer than k/2 consecutive vertices doesn't block the travel. Okay, so let's go back to the picture. So right, I'm starting at U. I can no longer travel this way because I deleted this vertex and the edge adjacent to it, but U is connected to in the original graph, it's connected to k/2 things to the right of it. So even though this is no longer an option, I can still travel in that direction just by skipping that vertex and then continuing on to V. Are you all convinced? Okay, so what that means is that we can find a UV path in G minus S. So that means that G minus S is connected for all sets S with the size of S less than K. So kappa of G is at least K. And that finishes the proof. Okay, are there questions about the proof? Okay, yeah, so we proved that it's greater than or equal to K, but we also previously proved less than or equal to, yeah. Other questions?
The minimum degree less than variable K. If it's not K, do they all have a degree K?
Yeah, yeah, they all, wait, let's go back to, yeah.
They all have degree K, why do we have to do like both sides of the proof? Like why can we just say,
Because, okay, so saying that it has degree K, so that tells me if I deleted all of the vertices that it's adjacent to, that would definitely disconnect the graph, right? But is it possible that there's a smaller disconnecting set? Yeah, because then that would give you your kappa of G. No, we just showed that you can't have a smaller disconnecting set. So we took a set S that had size less than K. So in this case, 3 vertices. And we showed that there's always a path between any, yeah. So that it's still connected if you delete fewer than K. Those are good questions. Other questions? Okay, so that was vertex connectivity. So there's also an idea of edge connectivity that's similar, and we'll so I'm gonna define edge connectivity and then we'll say how they're related. Okay, so So for the definition, a disconnecting set of edges is a set F of the edges such that G minus F has more than one component. And then we'll say a graph is K edge connected if every disconnecting set has at least K edges. So it's K edge connected. If every disconnecting set has at least K edges. And then the edge connectivity is the minimum size of a disconnecting set. And this is written as kappa prime of G. So kappa is vertex connectivity and then kappa prime is edge connectivity. Okay, and then there's one other thing. So there's one just common type of disconnecting set, which is called an edge cut. So given S and T subsets of the vertices, I'm gonna let brackets ST denote the set of edges that has one endpoint in S and one endpoint in T. So this is edges having one endpoint in S and one in T. Then an edge cut is an edge set of the form S, comma S bar, where S bar is just the complement. So V of G minus S. So with this, if I just take all of the vertices and move some to one side and some to the other side and delete all of the edges that are going between them in the middle, that is called an edge cut. And that's an example of a disconnecting set. Okay, so let's do an example. Okay, so in this graph, what's an example of an edge cut and a disconnecting set? So let's get an edge cut and a disconnecting set. So for an edge cut, all I need to do is just partition the vertices in any way I like. So for example, I could say, this is one set of vertices, this is another set of vertices, and then the edges that go between them, which would then be all of these edges, would form an edge cut. Okay, so is every edge cut a disconnecting set?
Yes.
Yes, so because it will disconnect the sets S and S bar. Does that make sense? So then what about the other way? Are disconnecting sets always edge cuts? So, okay, yeah, so what can happen? So let's start with a disconnect, sorry, and let's start with an edge cut. So so this was our example of an edge cut. So this is a disconnecting set, but I can also form a disconnecting set by just like deleting another edge, for example. So like, let's add this edge to our set. That's no longer an edge cut, but it's still a disconnecting set.
They have to contain.
Yeah, so we'll prove, yeah, we're about to prove every minimal disconnecting set is an edge cut. Yeah. So exactly what you just said. Yeah, so are disconnecting sets edge cuts? So the answer is no, they can contain extra edges. Okay, so let's prove the following. So we'll have a proposition. It says every minimal disconnecting set is an edge cut. So I'll give you all some time to think about the proof and then we'll discuss. So basically my hint show a disconnecting set contains an edge cut. And then the minimality will imply equality. Okay, so let's let F be a minimal disconnecting set. So why does F contain an edge cut? So if it's a disconnecting set, that means that after deleting it, I have more than one component, right? So let's let H be one of the components. Of G minus F. Okay, so what about the edges that go from H elsewhere? Yeah.
I have a question about like how this relates to the definition of disconnecting set. Because we said that if the graph is very disconnected, then any set is a disconnecting set. So how does this apply there?
And then a minimal disconnecting set would be the empty set, which is an edge cut. Because it's like vertices, one set is vertices and the other set is empty set. There's no edges going between those two, yeah. Yeah. No, it's good to think through these like edge case type of things just to like double check that your statement is like correct and stuff. Yeah. That's a good question. Okay, so if H is one component of G minus F, then I'm gonna claim that the edges in vertices of H, comma, the complement of that has to be contained in F. Do you guys believe this? Because like, so after deleting the vertices, or sorry, after deleting the edges in F, H is disconnected from everything else. So any edge that went from H to somewhere else has been deleted. And that's exactly what these vertices are. Okay, so our disconnecting set contains an edge cut, but then since the disconnecting set is minimal, this implies that F actually has to equal VH bar. Okay, are there questions? So going back to edge connectivity, so we're looking for the minimum size of a disconnecting set. So then it's good enough to just look at the edge cuts. So we don't have to look at all disconnecting sets because we know that a minimal disconnecting set is an edge cut. So we can just look at the edge cuts. So maybe I'll just write that down. So when trying to determine kappa prime of G, it suffices to look at the edge cuts. S bar. Okay, so now we have a theorem. And this kind of relates three quantities. So one is kappa of G, the vertex connectivity. And this is going to be less than or equal to kappa prime of G, the edge connectivity. And this is less than or equal to delta of G, which this is like, we defined this forever ago. This is the minimum vertex degree. Okay, so we'll do this in two parts. We'll just prove this inequality first and this inequality second. So for the proof, okay, so why is inequality 1 true? Yeah.
You can disconnect the graph by removing all edges going out from the vertex or minimum vertex degree.
Yeah, so if the degree of some vertex is equal to delta of G, so that vertex has minimum degree, then so then the edges containing V, which is just written as V comma V of G minus V. This disconnects the graph. And has size delta of G. Okay, so when we're looking at kappa prime, we're looking for the minimum size of a disconnecting set, and this exhibits a disconnecting set that has size delta of G. So that means that kappa prime has to have size smaller than delta of G, or less than or equal to. Okay, does that make sense? So let's prove the second inequality. So we've sort of, back at the beginning of the lecture, we showed that kappa of G is less than or equal to the number of vertices of G minus 1. So why is this? In the complete graph, it's equal, and we showed that in the other cases, it was less than or equal to n of G minus 2. Or like stated differently, if I delete all but one vertex, then I only leave behind one vertex. And that was like one case that was part of the definition. Okay, so we have this inequality. So let's consider a smallest edge cut S comma S bar. Okay, so since this is a smallest edge cut, the size of this is equal to kappa prime of G. So the number of edges in S comma S bar is equal to kappa prime of G. Okay, so then, if every vertex of S is adjacent to every vertex of S bar, then what is the size of S comma S bar? Well, it would be S times S bar. And this number. So yeah, so we're just considering like how many edges could this possibly contain? So if I had every possible adjacency, then that would be S times S bar many edges. And my claim is that that number has to be greater than or equal to n of g minus 1, which we already know is greater than or equal to kappa of g. Okay, so why is this true? So like, what's the worst case scenario for this number is like, I've put all but one of the vertices in S, one vertex on the other side, and then this would be equal to n of g minus 1. But then if I start moving vertices over to the other side, that's only going to increase things because as I move a vertex over, it initially only had one edge, but then you move it to the other side and now it's picked up n minus 2 edges. Does that make sense? Okay, so this was like one case. So this is if every edge is present, then the proof is done because we already had this equality. So this is equal to kappa prime of g. So otherwise, I'm gonna consider an edge between, so some non-edge between S and S bar. So like, so let's take X in S and Y in S bar such that XY is not an edge. Okay, so I'm gonna draw a picture. So this is gonna be my S, and this is S bar, and then here's X, and here's Y, and then I'm gonna have some other vertices in each of these. And I'll also draw some edges between them really quick. Okay. So this is my sketch of the situation. So we've picked out X and Y so that XY is not an edge. Then I'm gonna let T consist of the neighbors of X that are in S bar. And okay, so let's let T consist of the neighborhood of X in S bar. and vertices of S minus X that have neighbors. In, wait, this can't be right. Oh yeah, this is fine. Okay, so this picture is just not complete. So maybe there's more vertices over here. Okay, so I'm gonna let T consist of the neighbors of X in S bar and vertices in S that have edges in S bar. Okay, so let me draw what T looks like. So, oops, so now it's no longer clear what X is. Okay, so this is my X. And this is Y. So then T, first we need the neighbors of X in S bar. So this is part of T. And then in S, I also need the vertices that have neighbors in S bar. This is also part of T. Okay. So basically what we're gonna try to do is exhibit a disconnecting set of vertices that has to be smaller than this edge cut. So that's like what we're working towards. So I'm gonna make the observation that every path from X to Y has to pass through T. So why is that? Given that, for example, there could be edges over here that I haven't drawn, so we don't know if this is like a bipartite graph or whatever. So why does every path from X to Y pass through T? Yeah,
At some point you have to go from S to S bar, and that's either to a neighbor of X, which is in T, or from a vertex in S, which is not X, which is also in T, that's the neighbor in S bar.
yeah. Yeah, exactly. Okay, so do we buy this claim that we always have to pass through T? Okay, so that tells me, oh yeah, question.
Is X T, because you're saying, T consists of vertices in S that have edges and.
No, I don't want, yeah, I don't want X to be part of T, so I'll exclude it. Yeah, good question. Okay, so T is a separating set. Okay, and so now I just want to argue that the size of T has to be fewer than the number of edges depicted here. So I'm gonna note that picking the edges from X to those vertices of T that are in S bar. So I'm gonna pick out these edges. Right, because everything in the S bar side was a neighbor of T, or sorry, everything in T that's on the right-hand side is a neighbor of X. So I'm just gonna pick out those edges. And picking one edge from each vertex of those in T that are on the S side to S bar. So now I need to make a selection. For each vertex on the left-hand side in red, I need to pick one edge going to the right-hand side. So let's say we pick that one, and that one. Okay, so we have these green edges. So this yields size of T many distinct edges that are in this separating set S bar. Thus, okay, so we had kappa prime of G. This was supposed to be equal to the size of S bar, which we now know has size greater than or equal to the size of T. And we know that T is a separating set, but it might not be the smallest one. So this has size greater than or equal to kappa of G. And that finishes the proof. Okay, so we are sort of running out of time. I was gonna, maybe we'll pick up here next time. So I was gonna have you guys give examples, just to kind of see when these inequalities are equalities and when they are strict inequalities, and go through a theorem about one condition that would imply equality between kappa and kappa prime. So we'll pick up with that next time. Yeah, I'll see you then. Yeah. Hey.